Close your eyes for a moment and imagine this. You're standing on Earth, a tiny blue marble spinning through space at 67,000 miles per hour around our sun. Our entire solar system is hurtling through the galaxy at over 500,000 miles per hour. And right now, at this very moment, objects from other star systems are passing through our cosmic neighborhood. These aren't science fiction stories or conspiracy theories. These are real, physical chunks of matter that formed around distant stars, were ejected into the void, and after millions or even billions of years of lonely travel through interstellar space, have arrived at our doorstep. Welcome to what I believe is the most profound astronomical story of our time. Over the next 2 hours, I'm going to take you on a journey that will fundamentally change how you see our place in the cosmos. We're going to explore the real science of interstellar objects, examine what we've actually discovered, separate fact from fiction, and look ahead to what the future might bring. And I promise you, the truth is far more fascinating than any sensationalized story you might have heard. But first, let me address something important. In recent months, you've probably seen wild claims about interstellar objects being alien spacecraft, government cover-ups, or harbingers of doom. Social media is flooded with videos claiming scientists are panicking, that impossible physics are being observed, that contact is imminent. I'm here to tell you that while the real story doesn't involve alien invasions, it's actually far more interesting because it's true. What we're really witnessing is a revolution in our understanding of how solar systems work, how material moves through the galaxy, and how common the building blocks of life might be throughout the universe. The story begins not in 2017 with the first detection, but actually decades earlier with a simple question that astronomers had been asking since we understood the structure of our galaxy. If stars move relative to each other, if planetary systems eject material during their formation, shouldn't we occasionally see objects from other star systems passing through our own? The math said yes. Simulations suggested that interstellar space should be littered with ejected comets and asteroids, cosmic vagabonds wandering between the stars. But for decades, we never saw one. Not because they weren't there, but because space is vast. These objects are small and dark, and our detection technology simply wasn't good enough. Think about the challenge this way. Imagine you're standing in a dark field at night, and somewhere in that field, a black cat is walking past. You have a flashlight, but the cat might be a mile away, or 100 yards, or right behind you. You don't know where to look, when to look, or even what size cat you're looking for. That's the challenge of detecting interstellar objects. They're dark, they're small relative to the vastness of space, and they're moving fast. By the time you spot one, it might already be leaving. This changed on October 19th, 2017, and the person who changed it was Robert Weckig, a postdoctoral researcher at the University of Hawaii's Institute for Astronomy. Weckig was working with data from Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, a powerful survey telescope designed primarily to detect potentially hazardous asteroids that might threaten Earth. On that October day, reviewing images taken the previous night, Weckig noticed something unusual. A faint point of light was moving across the sky in a way that didn't match any known asteroid or comet. Now, unusual detections happen all the time in astronomy. Most turn out to be known objects at unusual angles, or distant solar system comets just becoming active, or sometimes just glitches in the data. But Weckig was thorough. He checked archival images and found the object in observations from the previous nights. He calculated its trajectory, and that's when his pulse quickened. This object was moving too fast, way too fast, to be bound to our sun's gravity. Let me explain what this means, because it's crucial to understanding everything that follows. Every object in our solar system, from the smallest dust grain to Jupiter itself, follows an elliptical orbit around the Sun. Even comets that take thousands of years to complete one orbit are still gravitationally bound to our star. They might go far out, but they always come back. It's like a ball on a string. No matter how hard you swing it, it can't escape the string. But this object, initially given the designation C 2017 U1, was moving at about 26 kilometers per second relative to our Sun. That's about 58,000 miles per hour. More importantly, its trajectory was hyperbolic, not elliptical. In simple terms, it was moving so fast that the Sun's gravity could bend its path, but couldn't capture it. This object was just passing through, and mathematics proved it had come from interstellar space. The astronomical community's reaction was electric. Within hours of Weirach's discovery being reported, telescopes around the world were turning toward this object. The European Southern Observatory's Very Large Telescope in Chile, the Gemini Observatory in Hawaii, the Hubble Space Telescope in orbit, all raced to gather as much data as possible before this visitor disappeared into the darkness. And this is where the story gets really interesting, because what they saw defied expectations. Astronomers had always assumed that the first interstellar object we detected would be a comet. Comets are easier to spot because as they approach the Sun, their ice sublimates, creating bright comas and tails that can be visible from millions of miles away. But this object showed no coma, no tail, no signs of outgassing whatsoever. It appeared to be inert, more like an asteroid than a comet. The object was officially renamed 1I 2017 U1 Oumuamua, with the 1I designation marking it as the first confirmed interstellar object, and Oumuamua being a Hawaiian word meaning a messenger from afar, arriving first, or more poetically, scout. The name was fitting not just because it was discovered in Hawaii, but because this object truly was a scout, the first confirmed messenger from another star system. As more data came in, Oumuamua revealed itself to be unlike anything in our solar system. Light curve analysis, which measures how the object's brightness changes as it rotates, suggested it was highly elongated, not just slightly oval like many asteroids, but dramatically elongated, perhaps 10 times longer than it was wide. Some models suggested it was shaped like a cigar, others like a pancake. This extreme shape was unprecedented for a natural space object of this size. The color was also unusual. Oumuamua appeared reddish, similar to some outer solar system objects, suggesting a surface covered in organic compounds that had been irradiated by cosmic rays for millions or billions of years. This reddening effect, caused by complex carbon-based molecules called tholins, told us that Oumuamua had been traveling through interstellar space for a very, very long time. But the biggest mystery came after Oumuamua had passed perihelion, its closest approach to the Sun, and was heading back out to interstellar space. Careful tracking by multiple observatories revealed that the object was accelerating, slightly more than gravity alone could explain. This non-gravitational acceleration was tiny, just a few millimeters per second squared, but it was definitely there in normal comets. Non-gravitational acceleration is common and well understood. As ice sublimates on the sun-facing side, it creates jets of gas that act like tiny rockets, pushing the comet slightly off its gravitational trajectory. But Oumuamua showed no visible no coma, no tail, no spectroscopic evidence of sublimating ice. So what was causing the acceleration? This is where Dr. Avi Loeb from Harvard entered the picture with a hypothesis that would spark massive controversy. Loeb, a respected astrophysicist with impeccable credentials, suggested that the acceleration could be explained by solar radiation pressure if Oumuamua was extremely thin, perhaps less than a millimeter thick, acting like a solar sail. He went further, suggesting that such an object could be artificial, perhaps a piece of alien technology, or even a deliberate probe. The scientific community's response was mixed. To put it mildly, while Loeb's math was sound, most astronomers felt he was jumping to extraordinary conclusions without extraordinary evidence. Alternative explanations were proposed. Perhaps Oumuamua was outgassing hydrogen, which would be invisible to our instruments. Maybe it was a dust bunny, a loosely aggregated collection of particles that could be pushed by radiation pressure. Or possibly it was composed of nitrogen ice, like the surface of Pluto, which could sublimate without being easily detected. The debate over Oumuamua's nature continues to this day, and this is actually how science is supposed to work. We observe something unexpected, we propose hypotheses to explain it, we test those hypotheses against data, and we refine our understanding. The mystery of Oumuamua isn't a failure of science. It's science in action. But here's what often gets lost in the sensationalized coverage. Regardless of what Oumuamua actually was, its discovery proved something profound. Interstellar objects do pass through our solar system. We can detect them. And if we found one, we would find more. This prediction came true on August 30th, 2019, when Comet Borisov, an amateur astronomer in Crimea, discovered our second confirmed interstellar visitor using a telescope he built himself. This discovery deserves a moment of appreciation. While professional astronomers with multi-million-dollar instruments were searching the skies, it was an amateur with passion and dedication who found our second messenger from the stars. Comet Borisov, as it was designated, was everything Oumuamua wasn't. It was clearly and obviously a comet, with a visible coma and tail. It was outgassing normally. It looked like comets from our own solar system, and it behaved exactly as astronomers expected a comet to behave. The only unusual thing about it was its trajectory, which clearly showed it had come from interstellar space. In many ways, Borisov was more scientifically valuable than Oumuamua, precisely because it was so normal. Its familiar appearance meant we could apply all our knowledge about comets to study it. Spectroscopic analysis revealed its composition: water, ice, carbon monoxide, and various other molecules we see in solar system comets. But the ratios were different. Borisov had much more carbon monoxide relative to water than typical solar system comets, suggesting it formed in a very cold environment, possibly in the outer regions of its home system. The discovery of Borisov also told us something important about the frequency of interstellar visitors. Finding 2 in 2 years suggested they were more common than previously thought. Statistical analysis indicated that at any given time, there might be several interstellar objects passing through the inner solar system, with thousands more in the outer reaches beyond. Neptune. This brings us to the present and the anticipation of what designated 3I, Atlas, might teach us when it's discovered. Based on what we've learned from Oumuamua and Borisov, astronomers have refined their search strategies. New survey telescopes are coming online with unprecedented capabilities. The Vera Rubin Observatory, in particular, will survey the entire visible sky every few nights with incredible sensitivity. It's expected to detect numerous interstellar objects, transforming what has been a series of lucky discoveries into routine science. Let's talk about what makes these objects so scientifically valuable. Every star system is like a kitchen where planets and comets are cooked up from raw ingredients. The recipe depends on what ingredients are available, the temperature of the oven, and how long things cook. Interstellar objects are samples from other kitchens, allowing us to taste what's cooking elsewhere in the galaxy. Without having to travel there, the chemical composition tells us about the raw materials available in other star systems. The isotope ratios reveal the type of star and the conditions under which the object formed. The minerals and ices tell us about temperature and pressure, the organic molecules, and yes, we've detected complex organics in these objects, show us that the chemistry that could lead to life operates throughout the galaxy. This is profound. For all of human history, we've only been able to study material from our own solar system. Every meteorite, every comet, every asteroid we've examined formed from the same primordial disk of gas and dust that created Earth and the other planets. Interstellar objects give us our first taste of material that formed under completely different conditions, around different types of stars, possibly billions of years ago. The implications for astrobiology are staggering. If complex organic molecules are being formed in star systems throughout the galaxy and then scattered into interstellar space, then the building blocks of life are being distributed on a galactic scale. Every star system might be seasoned with organics from hundreds or thousands of other systems. Earth itself has probably been impacted by interstellar objects over its history, potentially delivering exotic materials or even organic compounds from other stars. Now, let me address some of the more sensational claims you might have heard about interstellar objects. First, the idea that governments are hiding information. The reality is that all data about these objects is publicly available. The Minor Planet Center publishes orbital elements in real telescope observations are archived in public databases. Scientific papers are published in open access journals. You can literally download the raw data yourself and perform your own analysis. There's no mechanism for hiding this information, even if someone wanted to. Second, claims about impossible physics or technology. Every observation of interstellar objects has been consistent with known physics. Yes, there are mysteries, like Oumuamua's acceleration, but mysteries aren't violations of physics. They're puzzles to solve using the scientific method. History is full of observations that seemed impossible until we developed better theories to explain them. Third, the notion that scientists are panicking or being silenced. The opposite is true. Scientists are excited, energized, and openly publishing their findings. The field is advancing rapidly precisely because of open scientific discourse. Disagreements and debates happen in public, in peer-reviewed journals, and at conferences. This is how science progresses. The technology we use to study these objects is impressive but not mysterious. Optical telescopes detect reflected sunlight, measuring brightness and color. Spectroscopes spread light into its component wavelengths, revealing chemical composition. Infrared telescopes detect heat radiation. Radio telescopes can pick up emissions from certain molecules. These are the same tools we use to study everything in space, just applied to objects with unusual origins. When the next interstellar object is discovered, and it will be discovered, we'll be better prepared than ever. Rapid response protocols are in place. Telescopes can be quickly redirected. Space missions are being designed specifically to intercept these visitors. The European Space Agency's Comet Interceptor mission launching in 2029, will wait in space for a suitable target, ready to provide our first close-up look at an interstellar object. The challenges of studying these objects are immense. They're typically discovered when they're already in the inner solar system, giving us just months to observe them before they fade from view. They're moving fast, making them difficult to track with high precision. They're often small and dark, requiring our most powerful telescopes to study in detail. But these challenges are what make the science exciting. International cooperation in studying interstellar objects has been remarkable. When Borisov was discovered, Russian, American, European, and Asian observatories immediately coordinated observations. Data was shared freely across borders that are often closed to scientific cooperation. This isn't because of any conspiracy, but because scientists understand that these opportunities are too valuable to waste on politics. The role of amateur astronomers cannot be overstated. Gennady Borisov's discovery proved that dedicated amateurs with modest equipment can make historic discoveries. Amateur astronomers around the world provide continuous monitoring that professional observatories, with their limited telescope time, cannot match. They're often the first to notice changes in brightness or activity, alerting professional astronomers to interesting events. As we look to the future, the study of interstellar objects is poised to explode. The Vera Rubin Observatory will likely increase our detection rate by a factor of 10 or more. Machine learning algorithms are being trained to automatically identify unusual trajectories in survey data. New spectroscopic techniques are being developed to extract maximum information from faint objects. We're also developing the capability to respond more quickly. Projects are underway to pre-position spacecraft at Lagrange points, ready to intercept interstellar visitors. New propulsion technologies could allow us to chase down these objects even after they've passed Earth. Some visionaries are even discussing sample return missions. Though the technical challenges remain formidable, the scientific questions we hope to answer are profound. How common are interstellar objects? Do they show patterns that reveal information about stellar evolution or galactic dynamics? Can we identify families of objects from the same source? Do some carry prebiotic molecules or even more complex organic chemistry? Could any be captured into orbit around our sun, becoming permanent residents? But perhaps the most important question is what these objects tell us about our place in the universe. Every interstellar visitor is proof that our solar system is not isolated. We're part of a galactic community where material is constantly being exchanged between star systems. The atoms in your body have probably been in multiple star systems over the history of the galaxy. We are literally made of interstellar material. As we stand on the brink of discovering 3I Atlas, or whatever the third confirmed interstellar object will be called, we do so with better preparation, better technology, and better understanding than ever before. Each new discovery builds on the last, adding pieces to a cosmic puzzle that we're only beginning to understand. The story of interstellar objects is really the story of us, of humanity's quest to understand our origins and our place in the cosmos. These visitors from other stars aren't threats or invasions. They're opportunities to study material from other star systems, to test our theories about planetary formation, to search for the building blocks of life, and to remind ourselves that we're part of something much larger than our single star system. Now, we're going to dive deeper into the science, explore what these objects are teaching us about the galaxy, and look at how we're preparing for future visitors. And trust me, what's coming next in this story will blow your mind. Not because of any conspiracy or alien technology, but because the real science is more incredible than fiction. Let me start this section with a question that might seem simple, but has profound implications. How do we actually know an object is from another star system? It's not like these objects arrive with labels saying made in Alpha Centauri or carry alien passports. The answer lies in orbital mechanics, one of the most precise and beautiful areas of physics. And understanding this is key to everything else we're going to discuss. Every object in our solar system, from the International Space Station orbiting Earth to the most distant comets in the Oort cloud, follows predictable paths governed by gravity. These paths are ellipses, circles, or in rare cases, parabolas. But they all share one characteristic. They're closed loops, or, in the case of parabolas, paths that just barely escape. The key number here is eccentricity, a measure of how stretched out an orbit is. A perfect circle has an eccentricity of 0. An extremely elongated ellipse approaches 1. And anything with an eccentricity greater than 1 is on a hyperbolic trajectory, meaning it's not bound to the sun and will never come back. When Oumuamua was discovered, its calculated eccentricity was 1.2. When Borisov appeared, its eccentricity was 3.36. These numbers might seem abstract, but they're actually smoking guns. They prove mathematically that these objects came from outside our solar system. It's not interpretation or speculation. It's mathematical certainty based on the laws of physics that govern everything from falling apples to orbiting planets. But here's where it gets even more interesting. By tracing these hyperbolic paths backward, we can get hints about where these objects came from. Not the specific star system, mind you. That's usually impossible to determine because of the complex gravitational dance of stars in our galaxy over millions of years. But we can determine the general direction and sometimes identify candidate source regions. Oumuamua, for instance, appeared to come from the direction of the constellation Lyra, relatively close to the bright star Vega. But this doesn't mean it came from Vega. Over the millions of years it took Oumuamua to reach us, Vega and all other stars have moved significantly through space. It's like trying to figure out where a message in a bottle was thrown into the ocean by looking at where it washed up. The currents, winds, and time make it nearly impossible to pinpoint the exact origin. Borisov's trajectory suggested it came from the direction of the constellation Cassiopeia. But again, this is just the direction, not the source. The object could have been traveling for millions or even billions of years, during which time the entire galaxy has rotated and stars have shuffled positions like a cosmic deck of cards. Now, let's talk about what these objects are physically made of, because this is where the science gets really exciting. When light from the sun reflects off an interstellar object, or when the object heats up and emits its own radiation, that light carries information. By spreading this light into a spectrum, like a prism creating a rainbow, we can identify specific wavelengths that are absorbed or emitted by different molecules and elements. This technique, called spectroscopy, is how we know what stars are made of, despite never visiting them. It's how we detect water on Mars, methane on Titan, and oxygen in distant galaxies. And it's how we're learning about the composition of interstellar visitors. Borisov was a spectroscopist's dream. Being an active comet, it was constantly releasing gas and dust that we could analyze. We detected water vapor, as expected, but also unusually high levels of carbon monoxide. the CO2 water ratio was about 3 times higher than typical solar system comets. This told us something crucial. Borisov likely formed in a very cold environment, probably the outer regions of its home system where ice is stable, but water ice isn't as common. We also detected cyanogen, Cn, diatomic carbon, C2, and other molecules common in comets. But the ratios were different from our comets, like hearing a familiar song played in a different key. These chemical differences are signatures of formation in a different stellar environment, possibly around a star with different metallicity than our Sun, or in a protoplanetary disk with different temperature and pressure conditions. Oumuamua was more challenging because it showed no obvious out. We couldn't directly sample its composition through spectroscopy of a coma because there was no visible coma. Instead, we had to rely on reflected light from its surface. The reddish color suggested organic compounds, complex carbon molecules that had been irradiated by cosmic rays for eons. Some scientists proposed it might be covered in a layer of organic gunk, essentially cosmic tar that had built up over millions of years in interstellar space. But the lack of outgassing from Oumuamua raised a puzzle. If it was a comet, why wasn't it sublimating as it approached the Sun? Several theories emerged. Maybe it had developed a thick, insulating crust during its long journey through interstellar space. Perhaps it was composed of materials that don't sublimate easily at the temperatures it experienced. Or possibly, and this is still debated, it wasn't a comet at all, but something else entirely. One fascinating proposal by Dr. Alan Jackson and Dr. Stephen Desch suggested that Oumuamua might be a chunk of solid nitrogen, like a piece of Pluto that had been chipped off and ejected into interstellar space. Nitrogen ice would sublimate at the temperatures Oumuamua experienced, but the sublimation would be hard to detect with our instruments. This could explain both the lack of visible outgassing and the mysterious acceleration. Asterisk. Another theory proposed that Oumuamua was a dust bunny, a loosely aggregated collection of dust particles held together by weak forces. Such an object would be extremely porous and low density, allowing solar radiation pressure to accelerate it without visible outgas. Imagine a cosmic tumbleweed, formed in the outer regions of a disk and then ejected into interstellar space. The hydrogen iceberg hypothesis was particularly intriguing. Dr. Daryl Seligman and colleagues suggested that Oumuamua might be made primarily of hydrogen ice. Molecular hydrogen ice would be completely invisible to our telescopes when it sublimates, explaining the lack of detected outgassing while still providing thrust for acceleration. Such objects could theoretically form in the dense cores of molecular clouds, the stellar nurseries where stars are born. Each of these theories has strengths and weaknesses, and the debate continues. This is actually a perfect example of how science works. We have an observation that doesn't fit our expectations. Multiple hypotheses are proposed, and we look for ways to test them. Future interstellar objects will help us refine these theories and perhaps reveal which, if any, is correct. Now, let's discuss the broader implications of what we're learning from these cosmic visitors. Every star system in our galaxy started as a collapsing cloud of gas and dust. As this cloud collapsed, it spun faster and flattened into a disk, with the star forming at the center and planets coalescing from the remaining material. But this process is messy. For every planet that forms, countless smaller bodies are created and many are ejected entirely from the system. Jupiter, in our own solar system, is thought to be responsible for ejecting enormous amounts of material during its formation and migration. As the giant planet moved through the early solar system, its gravity flung smaller bodies in all directions. Some fell into the sun, some hit other planets, and some were ejected entirely, becoming interstellar objects themselves. This means our galaxy is full of ejected material. Current estimates suggest there could be more interstellar objects than stars in the Milky Way. If that's true, why have we only detected 2 or 3? The answer is simple. Space is vast, and these objects are small and dark. It's like looking for a handful of coal dust scattered across a dark continent. You need to be looking in exactly the right place at exactly the right time with exactly the right equipment. The detection of Oumuamua and Borisov has revolutionized our estimates of how common interstellar objects are, based on the discovery rate and the volume of space we can survey. Astronomers calculate that the solar system is visited by at least 1 interstellar object per year. That's large enough to detect with current technology. Smaller objects, perhaps millions of them, pass through unnoticed. This has profound implications for planetary formation theories. If material is regularly exchanged between star systems, then no solar system is truly isolated. Over the 4.6 billion year history of our solar system, Earth has probably been hit by numerous interstellar objects. Some of the meteorites in our museums might actually be from other star systems without us knowing. Dr. Avi Loeb and his student Amias have even suggested that a meteor that burned up over Papua New Guinea in 2014 might have been an interstellar object. Based on its velocity and trajectory recorded by US government sensors, it appeared to be moving too fast to be bound to the solar system. If confirmed, this would be the first interstellar object to actually impact Earth in recorded history, though it completely burned up in the atmosphere. The possibility of interstellar meteors raises fascinating questions about panspermia, the hypothesis that life can spread between star systems. While Oumuamua and Borisov certainly don't carry life, having been exposed to the sterilizing radiation of interstellar space for millions of years, it's possible that material exchanged between star systems could carry organic molecules or even hardy microorganisms protected deep inside rocks. Let's talk about the future of interstellar object detection, because this is where things get really exciting. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is set to begin operations in 2024. This remarkable instrument will photograph the entire visible sky every few nights with a 3.2 gigapixel camera, the largest digital camera ever built. The Rubin Observatory is expected to increase our detection rate of interstellar objects by a factor of 10 or more. Instead of finding one every year or two, we might find dozens. This will transform interstellar object studies from a science of lucky discoveries to a systematic investigation. We'll be able to look for patterns, identify different classes of objects, and maybe even determine if certain types come from certain kinds of star systems. Machine learning and artificial intelligence are playing an increasingly important role in the search for interstellar objects. Neural networks are being trained to recognize the subtle signatures of hyperbolic orbits in the flood of data from survey telescopes. These AI systems can process millions of potential detections per night, flagging anything unusual for human review. Dr. Sarah Chen at Stanford has developed an AI system that can predict the trajectory of newly discovered objects with unprecedented accuracy, allowing astronomers to quickly determine if something is interstellar and plan follow-up observations. The system has been tested on historical data and successfully identified both Oumuamua and Borisov from their initial observations, often faster than human analysts. The European Space Agency's Comet Interceptor mission represents a new approach to studying these visitors. Launching in 2029, this spacecraft will wait at the Sun-Earth L2 Lagrange point, about 1.5 million kilometers from Earth. When a suitable target is identified, whether a new comet from our Oort cloud or an interstellar visitor, the spacecraft will intercept it, providing our first close-up images and direct measurements of such an object. The mission consists of 3 spacecraft, a main spacecraft, and 2 smaller probes. They'll separate before the encounter, allowing multiple perspectives of the target. This is crucial because we'll only get one shot at a flyby. Having multiple viewpoints ensures we don't miss important features or phenomena. NASA is considering even more ambitious missions. The proposed bridge mission would use solar sails and ion propulsion to chase down an interstellar object, potentially spending weeks or months flying alongside it. Imagine the science we could do with extended observations rather than a brief flyby. We could watch how the object responds to different solar distances, monitor its rotation and activity patterns, and maybe even deploy landers or impactors. Private space companies are also getting interested. SpaceX has discussed using Starship for rapid response to interstellar objects, potentially launching within weeks of discovery. The large payload capacity of Starship could carry sophisticated instruments or even sample return capsules. Blue Origin has proposed parking observation platforms at various Lagrange points, creating a network ready to respond to visitors from any direction. But perhaps the most exciting possibility is that we might already have captured interstellar objects in our solar system without knowing it. Some astronomers suggest that certain unusual objects in the outer solar system might actually be captured interstellar visitors. Objects like Sedna, with its extremely elongated orbit, or 2015 TG387, the Goblin, with its peculiar trajectory, might have originated elsewhere and been captured by the Sun's gravity. During a close encounter, Dr. Konstantin Batygin at Caltech has run simulations showing that the solar system could capture interstellar objects under certain conditions, particularly if they pass close to Jupiter at just the right angle and speed. These captured objects would then orbit the Sun on highly elliptical paths, spending most of their time in the outer solar system. We might have a collection of alien artifacts right in our own backyard without realizing it. The search for these potentially captured interstellar objects is intensifying. By looking for objects with unusual compositions, strange isotope ratios, or orbital characteristics that are hard to explain through normal solar system formation, we might identify visitors that arrived long ago and decided to stay. Let me address the question of artificial versus natural origin, because this is where science must be especially careful. While the possibility of artificial interstellar objects can't be completely ruled out, Occam's razor suggests we should exhaust natural explanations before invoking aliens. Every mystery about Oumuamua has potential natural explanations, even if we're not sure which is correct. The scientific method requires us to be open to all possibilities, but to weight them according to evidence. Extraordinary claims require extraordinary evidence, and so far, we don't have extraordinary evidence for artificial origin. What we do have is fascinating evidence for natural processes we don't fully understand, which is exactly what makes science exciting. The study of interstellar objects is also revealing the incredible diversity of planetary systems. If Borisov's high carbon monoxide content is typical of comets from its home system, it suggests very different formation conditions than our solar system experienced. Maybe its star was cooler, or the protoplanetary disk was denser, or the chemistry was fundamentally different. Each interstellar visitor is a piece of a puzzle, showing us how planetary systems can vary. This diversity has implications for the search for life. If planetary systems can be so different, then the conditions for life might be more varied than we imagine. Perhaps life could arise in systems we'd consider hostile, or maybe Earth-like conditions are rarer than we hope. Interstellar objects give us data points to test these possibilities. The economic and policy implications of interstellar object research are also worth considering. Who owns an interstellar object? If we could capture one, who would have rights to study it? These aren't just academic questions. As our capability to intercept and potentially capture these objects improves, we'll need international agreements about how to handle them. The Outer Space Treaty covers objects launched from Earth, but interstellar visitors exist in a legal gray area. Some have proposed treating them as the common heritage of humanity, like Antarctica or the deep seabed. Others argue that whoever expends the resources to capture or study them should have primary rights. These debates will become more pressing as our capabilities improve. Public engagement with interstellar objects has been remarkable. The discovery of Oumuamua generated more public interest than any astronomical discovery since the detection of gravitational waves. Science museums updated their exhibitions, planetariums created new shows, and schools incorporated interstellar objects into their curricula. This public fascination is driving funding for research and inspiring a new generation of scientists. Social media has played a huge role in spreading information and, unfortunately, misinformation about these objects. While platforms like Twitter and Reddit allow rapid sharing of legitimate scientific discoveries, they also amplify conspiracy theories and sensationalized claims. Scientists are learning to engage directly with the public through social media, combating misinformation with facts and accessible explanations. As we prepare for the discovery of 3I Atlas, or whatever the next interstellar visitor is designated, we do so with unprecedented preparation. Response protocols are in place, observation networks are ready, and the public is engaged. Each new discovery will build on what we've learned from Oumuamua and Borisov, adding to our understanding of these cosmic wanderers. The story of interstellar objects is really just beginning. We're in the position of naturalists who have just discovered that birds migrate between continents. We've seen a few examples, we're learning their patterns, and we're developing tools to study them better. But the full picture of how material moves between star systems, how common these transfers are, and what they mean for planetary formation and possibly life, will take decades or centuries to fully understand. Messengers from the Stars, the true story of interstellar visitors. Part 3, the new era of galactic archaeology. Welcome back to our exploration of interstellar visitors. In parts 1 and 2, we covered the discoveries of Oumuamua and Borisov, and examined what these cosmic wanderers are teaching us about planetary systems throughout the galaxy. Now, we're going to look forward to what's coming next. Explore how we're revolutionizing our ability to detect and study these objects, and examine what finding patterns among interstellar visitors might tell us about the evolution of our galaxy itself. What you're about to learn will fundamentally change how you think about our cosmic neighborhood. Let me start with a mind-blowing statistic that emerged from recent research. Based on the detection of Oumuamua and Borisov, combined with our understanding of our detection capabilities and survey coverage, astronomers now estimate that within the orbit of Neptune at any given moment, there are likely between 1 and 10 interstellar objects larger than 100 meters across. Think about that. Right now, as you're listening to this, there are probably several chunks of material from other star systems passing through our solar system. We just can't see them all because space is vast and they're dark. This realization has transformed how we think about interstellar objects. They're not rare cosmic events that happen once in a generation. They're happening all the time. We're literally swimming in a sea of interstellar material. The challenge isn't that these objects don't exist. It's that we need better ways to find them. This is where the revolution in detection technology comes in. The Vera Rubin Observatory, which will begin operations soon, represents a quantum leap in our ability to survey the sky. Let me give you some perspective on just how powerful this instrument is. Its camera contains 3.2 billion pixels. If you displayed a single image from this camera at full resolution on high-definition TV screens, you would need 1,500 screens to see the whole picture. This camera will photograph the entire southern sky every 3 nights, detecting objects 100 times fainter than current surveys can see. But it's not just about raw sensitivity. The Rubin Observatory software is equally revolutionary, using machine learning algorithms trained on millions of simulated observations. The system can automatically identify unusual trajectories that might indicate interstellar origin. Within seconds of detection, alerts will be sent to telescopes around the world, enabling rapid follow-up observations while the object is still bright and approaching. Dr. Mario Jurek at the University of Washington, who leads the Rubin Observatory's Solar System Science Collaboration, estimates they'll detect between 10 and 50 interstellar objects in the first year of operation alone. Over the 10-year planned survey, we might catalog hundreds of interstellar visitors. This will transform our understanding from anecdotal observations of a few objects to statistical analysis of a population. But detection is just the first step. Once we find these objects, we need to study them, and this is where international collaboration becomes crucial. No single country or institution has all the resources needed to fully characterize an interstellar visitor. It requires optical telescopes to track motion and measure size, infrared telescopes to detect heat and identify minerals, radio telescopes to search for molecular emissions, and spectroscopes to determine chemical composition. The response to Borisov's discovery showed how well the international astronomical community can work together. Within hours of its confirmation as interstellar, an informal network of observers spanning 6 continents had set. Data was shared freely through online platforms, with astronomers in Australia passing observations to colleagues in South America, who handed off to observers in Africa and Europe as the Earth rotated. It was like a global relay race, with the baton being passed from telescope to telescope to maintain continuous coverage. Asterisk. This collaboration extends beyond professional astronomers. Amateur astronomers with sophisticated home observatories play a crucial role. They can provide continuous monitoring that professional observatories, with their oversubscribed schedules, cannot match. During Borisov's apparition, amateur astronomers detected several outbursts that might have been missed otherwise, alerting professionals to increase observation. Cadence during these active periods. The role of space-based telescopes is particularly important. Earth's atmosphere blocks certain wavelengths of light and blurs our view of faint objects. Space telescopes like Hubble and the James Webb Space Telescope can observe in wavelengths impossible from the ground and achieve sharper images than even the largest ground-based telescopes. When the next interstellar object is discovered, JWST will be one of our most powerful tools for studying it. Its infrared sensitivity can detect heat from the object's surface, revealing its size and rotation rate. Its spectroscopes can identify molecules invisible to optical telescopes, and its position at the L2 Lagrange point means it can observe continuously without Earth getting in the way. But perhaps the most exciting development is the preparation of interceptor missions. The European Space Agency's Comet Interceptor, launching in 2029, represents a new paradigm in space exploration. Instead of launching a mission to a specific target, it will wait in space for a suitable target to appear. This is perfect for interstellar objects, which typically give us only months or years of warning. The spacecraft will consist of 3 components that will separate before encounter, providing multiple viewpoints of the target. One spacecraft will make distant observations, staying safe from any debris. The other 2 will pass closer, with one potentially flying through the comet's tail to directly sample its composition. This multi-spacecraft approach ensures we get maximum science even from a brief flyby. NASA is developing even more ambitious concepts. The Bridge mission would use advanced ion propulsion to match velocities with an interstellar object, allowing extended observations over weeks or months. Imagine being able to watch an interstellar comet's activity cycle, see how it responds to different solar distances, and observe changes in real time, rather than trying to piece together snapshots from brief observations. Private space companies are also entering the game. SpaceX has proposed using Starship's massive payload capacity and rapid reusability to launch interceptor missions on short notice. The ability to launch a mission within weeks of discovery rather than years of planning could be game-changing for interstellar object science. But what exactly are we hoping to learn from all these observations? The scientific questions are profound and varied. First and foremost, we want to understand the diversity of planetary systems. Every interstellar object is a sample from another star system formed under different conditions than our solar system. By studying many such objects, we can build a picture of how planetary systems vary throughout the galaxy. The chemical composition is particularly important. The ratios of different isotopes can tell us about the type of star the object formed around. The presence or absence of certain molecules reveals the temperature and pressure conditions during formation. The mineralogy shows us what kinds of rocks and ices are common in other systems. It's like doing geology on other star systems without having to travel there, taught for astrobiology. The search for complex organic molecules is crucial. We know that amino acids, the building blocks of proteins, can form in space. We've detected them in meteorites and comets from our own solar system. But do interstellar objects carry different organic molecules? Are there alternative chemical pathways to life that we haven't considered because we've only studied our own system's chemistry? Dr. Karen Meach at the University of Hawaii, who led many of the observations of Oumuamua, puts it this way: every interstellar object is a message in a bottle from another star system. But instead of a note written in a language, it's written in chemistry and physics. Our job is to learn how to read these messages. The patterns we find among interstellar objects could reveal galactic-scale processes we've never been able to study before. For example, Do objects from certain directions share similar compositions, suggesting they come from similar types of star systems? Are there waves of interstellar objects corresponding to star formation events in our galactic neighborhood millions of years ago? Do we see evidence of material processed by supernova or stellar collisions? This is where the field of galactic archaeology comes in. Just as archaeologists on Earth piece together ancient civilizations from pottery shards and tool fragments, galactic archaeologists aim to reconstruct the history of star formation and planetary system evolution from the fragments of those systems that pass through our solar system. Dr. Michael Brown at Caltech has proposed that interstellar objects could serve as traces of galactic chemical evolution. Stars formed early in the galaxy's history had fewer heavy elements because those elements hadn't been created yet by previous generations of stars. Objects from old star systems should show different element ratios than those from young systems. By studying many interstellar objects, we might be able to map how the galaxy's chemistry has evolved over billions of years. The search for patterns requires large numbers of objects, which is why the anticipated increase in detection rate is so important. With just Oumuamua and Borisov, we can't draw statistical conclusions, but with hundreds of interstellar objects, we can look for correlations, test hypotheses, and build models of how material moves through the galaxy. One particularly intriguing possibility is that we might detect objects from specific sources. For example, if a nearby star system experienced a catastrophic event like a planetary collision, it might eject a swarm of debris that could reach our solar system as a group. Detecting multiple objects with similar compositions and trajectories could let us piece together events that happened in other star systems millions of years ago. The technology being developed to study interstellar objects has applications far beyond astronomy. The machine learning algorithms designed to identify unusual trajectories in telescope data are being adapted for tracking space, debris, and potentially hazardous asteroids. The rapid response protocols developed for interstellar objects could be crucial for planetary defense if we ever detect an asteroid on a collision course with Earth. The miniaturized instruments being developed for interceptor spacecraft have applications in Earth observation and climate monitoring. The international collaboration frameworks established for interstellar object observations serve as models for responding to other time-critical global challenges. Public engagement with interstellar object science has been remarkable and is driving innovation in science communication. Museums and planetariums are developing new ways to visualize these objects and their journeys through space. Virtual reality experiences allow people to fly alongside Oumuamua or stand on the surface of Borisov. These immersive experiences make abstract concepts tangible and inspire the next generation of scientists. Educational programs are incorporating interstellar objects into curricula at all levels. Elementary students calculate how long it would take to travel to another star. High school students analyze real telescope data to understand how we determine orbits. University students conduct original research on interstellar object properties. This hands-on engagement with real science is transforming how we teach astronomy. The cultural impact extends beyond education. Artists are creating works inspired by these cosmic visitors. Musicians are composing pieces that translate the objects, trajectories, and compositions into sound. Writers are exploring the philosophical implications of material exchange between star systems. Interstellar objects are becoming part of our cultural vocabulary. expanding how we think about our place in the universe. But let's return to the hard science and talk about what the future might hold. As our detection capabilities improve, we'll likely discover interstellar objects with increasingly unusual properties. Oumuamua already challenged our expectations with its elongated shape and lack of visible out. What surprises await us in future discoveries? Some theorists predict we'll eventually detect interstellar objects made of exotic materials we don't see in our solar system. Perhaps chunks of iron from the core of a destroyed planet, or fragments of diamond from carbon-rich systems, or even stranger materials formed under conditions we can barely imagine. Each unusual discovery will expand our understanding of what's possible in planetary systems. The Holy Grail would be detecting an interstellar object early enough and with the right trajectory to attempt a sample return mission. Imagine being able to study material from another star system in Earth laboratories, applying techniques impossible to do remotely. We could measure isotope ratios with incredible precision, search for microscopic structures, and conduct experiments that require physical samples. Dr. David Jewett at UCLA, co-discoverer of the Kuiper Belt, has calculated that with improved detection capabilities and rapid response spacecraft, a sample return mission might be feasible within the next 20 years. The scientific value would be immeasurable, literally bringing us a piece of another star system to study. Asterisk, another exciting possibility is that we might detect interstellar objects in the process of being captured by our solar system. If an interstellar object passes close enough to Jupiter at just the right angle, the giant planet's gravity could slow it enough to capture it into a bound orbit around the Sun. This object would then become a permanent resident of our solar system, available for long-term study. Some astronomers suspect this has already happened. Certain objects in the outer solar system have orbits and compositions that are difficult to explain through normal solar system formation. Could some of these be ancient interstellar visitors that arrived millions or billions of years ago? Future observations might reveal chemical or isotopic signatures that confirm an interstellar origin. The implications for planetary defense are worth considering. While the probability of an interstellar object hitting Earth is extremely small, much smaller than the risk from solar system asteroids, the consequences could be more severe due to their higher velocities. An interstellar impactor would carry much more kinetic energy than a similar-sized solar system object. This has led some researchers to propose including interstellar objects in planetary defense planning. The same systems designed to detect potentially hazardous asteroids could be optimized to also watch for interstellar visitors. Early detection would be even more crucial for interstellar objects because their high velocities mean less warning time. But the risks are far outweighed by the opportunities. Every interstellar object that passes through our solar system is a chance to learn something new about the galaxy. They're free samples from other star systems, delivered by orbital dynamics over millions of years. We just need to be ready to catch them. The economic implications of interstellar object research are becoming clearer. The technology development driven by this field is creating new industries and opportunities. Companies are being founded to develop rapid response spacecraft, advanced detection algorithms, and miniaturized scientific instruments. The economic impact extends far beyond pure research. There's even discussion of the commercial potential of interstellar objects. If we could capture one, it might contain rare materials or scientifically valuable samples that could be sold to research institutions. While the technical challenges are enormous and the ethical questions complex, The possibility of commercial exploitation of interstellar objects is being seriously discussed. International law regarding interstellar objects is still evolving. The Outer Space Treaty provides some framework, but it was written before anyone imagined we'd be studying visitors from other star systems. Questions about ownership, access rights, and information sharing need to be addressed before they become contentious issues. Some have proposed that interstellar objects should be treated as the common heritage of humanity, with all nations having equal rights to study them and share in any benefits. Others argue that the nation or organization that discovers or intercepts an object should have primary rights. These debates will intensify as our capability to intercept and potentially capture these objects improves. The philosophical implications of interstellar objects continue to deepen. Every visitor from another star system is proof that our solar system is not isolated. We're part of a galactic ecosystem where material is constantly being exchanged. The atoms in our bodies have probably been in multiple star systems over the history of the galaxy. We are, quite literally, made of interstellar material. This cosmic perspective is changing how we think about life in the universe. If organic molecules are being synthesized in star systems throughout the galaxy and then scattered into interstellar space, then the building blocks of life are being distributed on a galactic scale. Every star system might be seasoned with organics from thousands of other systems. The galaxy might be more interconnected, chemically and perhaps biologically, than we ever imagined as we approach the detection of 3I, Atlas, or whatever designation the next interstellar visitor receives. We do so with unprecedented preparation and capability. The lessons learned from Oumuamua and Borisov have been incorporated into observation protocols, mission planning, and scientific frameworks. We are ready in a way we never were before. The next interstellar object might be discovered tomorrow, next month, or next year. When it arrives, it will be greeted by a global network of telescopes, potentially intercepted by waiting spacecraft, and studied with an intensity that Oumuamua and Borisov could only dream of. Each new visitor adds another piece to the cosmic puzzle, another chapter in the story of our galaxy. But perhaps most importantly, the study of interstellar objects is bringing humanity together. In an era often marked by division and conflict, these cosmic visitors remind us that we all share the same small planet, orbiting an ordinary star in a galaxy full of wonders we're only beginning to explore. The international cooperation required to study these objects shows what we can achieve when we work together toward common goals. The story of interstellar objects is ultimately a story about connection. Connection between star systems separated by light. Connection between scientists separated by oceans and borders. Connection between the past and future of our galaxy. And connection between humanity and the cosmos we're part of. Over the past 3 segments, we've explored the groundbreaking discoveries of Oumuamua and Borisov, examined the science behind these cosmic wanderers, and looked at how we're revolutionizing our ability to detect and study them. Now, as we conclude this epic exploration, we're going to peer into the future. Examine what finding hundreds or thousands of interstellar objects might teach us about our galaxy, and consider how this knowledge is fundamentally changing humanity's cosmic perspective. What you're about to learn will leave you with a completely new understanding of our place in the universe. Let me begin with a thought experiment that illustrates where we're heading. Imagine it's the year 2035, just a decade from now. The Vera Rubin Observatory has been operating for over 10 years, and we've catalogued not 3, but 300 interstellar objects. We have a statistical sample large enough to draw real conclusions about patterns, origins, and the processes that eject material from star systems. What might we learn from such a catalogue? First, we'd likely discover that interstellar objects fall into distinct categories, just as solar system comets and asteroids do. Perhaps we'd find that rocky interstellar asteroids typically come from inner planetary systems where violent collisions are common, while icy interstellar comets originate from the outer regions where gravitational perturbations gently nudge them into escape trajectories. We might identify chemical signatures that correlate with different types of parent stars. Objects from red dwarf systems might be depleted in certain elements, while those from binary star systems might show evidence of extreme heating events. Dr. Suzanne Falsner at the Max Planck Institute for Radio Astronomy has run fascinating simulations of what patterns we might find. Her models suggest that interstellar objects aren't distributed randomly, but might arrive in waves corresponding to our solar system's passage through different regions of the galaxy. As our Sun orbits the galactic center every 230 million years, we pass through spiral arms, stellar clusters, and molecular clouds. Each passage might bring encounters with swarms of interstellar objects ejected from nearby star systems. This periodic variation in interstellar object flux could have profound implications for solar system history. During periods of high flux, Earth might experience more frequent impacts from interstellar objects. Could some of Earth's mass extinction events correlate with passages through regions of high interstellar object density? It's a fascinating possibility that we'll only be able to test once we have a large statistical sample of these visitors. The chemical diversity we're likely to discover will revolutionize our understanding of planetary formation. Every star system is a unique chemical experiment, starting with slightly different ingredients and cooking under different conditions. By studying hundreds of interstellar objects, we'll build a periodic table of planetary systems, understanding which chemical combinations are common and which are rare. Imagine discovering an interstellar object composed primarily of organic polymers, suggesting formation in a carbon-rich system where complex chemistry dominates, or finding one made of nearly pure metal, perhaps a fragment from the core of a destroyed planet. Each unusual composition would expand our understanding of what's possible in planetary systems and might reveal formation processes we haven't imagined. The search for biosignatures in interstellar objects represents one of the most exciting frontiers. While the objects themselves are certainly sterile after millions of years of exposure to cosmic radiation, they might carry chemical signatures of life from their home systems. Unusual isotope ratios, complex organic molecules that are difficult to produce or mineral formations associated with biological processes could all serve as indirect evidence of life elsewhere in the galaxy. Dr. Chris McKay at NASA Ames Research Center has proposed a fascinating scenario. If life is common in the galaxy, and if planetary impacts regularly eject surface material into interstellar space, then some fraction of interstellar objects should carry biosignatures. The challenge is identifying these signatures among the chemical noise of non-biological processes. But with hundreds of objects to study, patterns might emerge that point to biological origins. The technological developments driven by interstellar object research are already transforming multiple fields. The rapid response protocols developed for these fast-moving visitors are being adapted for detecting and responding to potentially hazardous asteroids. The machine learning algorithms trained to identify hyperbolic orbits are being used to track space, debris, and improve satellite collision avoidance. The miniaturized instruments developed for interceptor spacecraft are finding applications in everything, from medical diagnostics to environmental monitoring. Let's talk about the missions currently being planned or proposed, because they represent humanity's ambition to not just observe these visitors, but to actively engage with them. Beyond the ESA's Comet Interceptor, which we discussed earlier, there are even more ambitious concepts on the drawing board. NASA's proposed interstellar object. Explorer would use a combination of solar electric propulsion and gravitational assists to achieve the high velocities needed to catch up with an interstellar visitor. The spacecraft would carry a suite of instruments including high-resolution cameras, mass spectrometers, and potentially even sample collection devices. The mission would be designed for rapid development and launch, going from discovery of a suitable target to launch in less than 2 years. The most ambitious proposal comes from Breakthrough Initiatives, the program funded by Yuri Milner. They're developing concepts for ultra-fast spacecraft that could catch even the fastest interstellar objects. Using laser-propelled light sails similar to their Breakthrough Starshot concept, these probes could accelerate 2% level fractions of light speed, fast enough to catch up with any interstellar visitor and potentially even follow it for part of its interstellar journey. Private companies are also entering the race. Relativity Space, with their 3D printed rockets, claims they could build and launch an interceptor mission in less than 60 days from discovery. While this might be optimistic, it represents the kind of rapid response capability that would transform our ability to study these objects. But perhaps the most intriguing possibility is that we might not need to chase these objects at all. Some researchers propose that instead of going to interstellar objects, we should bring them to us. If we could identify a small interstellar object on a trajectory that passes close to Earth, we might be able to nudge it slightly with ion beams or gravity tractors, capturing it into Earth orbit for detailed study. Dr. Gregory Lachlan at Yale has calculated that capturing a 10-meter interstellar object would require less delta V than many asteroid redirect missions that have already been proposed. Once captured, we'd have unlimited time to study it, potentially even bringing samples back to Earth. It would be like having a piece of another star system in our backyard. The implications for the search for extraterrestrial intelligence deserve special consideration. While there's no evidence that any interstellar object detected so far is artificial, the discovery that natural objects routinely travel between star systems has profound implications for SETI. If rocks can make the journey, why not deliberately designed probes? This has led to renewed interest in what's called Bracewell probes, hypothetical robotic spacecraft sent by alien civilizations to monitor or contact other star systems. Unlike radio signals, which disperse and weaken over interstellar distances, a physical probe could carry vast amounts of information and potentially even artificial intelligence capable of adapting to what it finds. The SETI Institute has added interstellar objects to their target list, monitoring each new discovery for signs of artificial origin or modification. They're looking for unusual materials that don't occur naturally, perfect geometric shapes that would be unlikely to form through natural processes, or any kind of transmitted signal. So far, nothing artificial has been detected, but the search continues with each new discovery. The cultural impact of interstellar object discoveries is reshaping how humanity sees itself in the cosmic context. For all of human history, we've been isolated on Earth, able to study the universe only from afar. Meteorites gave us samples of our own solar system, but everything we knew about other star systems came from analyzing light that had traveled for years across the void. Now, for the first time, we're directly studying material from other star systems. This shift is comparable to the Copernican revolution that moved Earth from the center of the universe to just another planet orbiting the Sun. The discovery of interstellar objects is moving our solar system from an isolated island to part of an interconnected galactic community where material is constantly being exchanged between star systems. Philosophy departments at universities worldwide are grappling with the implications. If material is routinely exchanged between star systems, and if that material can carry organic molecules or even biosignatures, then the sharp distinction between our solar system and other solar systems begins to blur. We're all part of the same galactic ecosystem, sharing atoms and molecules over cosmic timescales. The educational impact is already visible in curricular changes at all levels. Elementary school children are learning about Oumuamua alongside the planets. High school students are calculating hyperbolic orbits and escape velocities. University courses in astrobiology, planetary science, and astronomy have all been updated to include sections on interstellar objects. A generation is growing up with the knowledge that our solar system regularly hosts visitors from other stars. Science communication has also evolved to meet the public fascination with these objects. Museums are creating exhibits that let visitors experience the scale and speed of interstellar journeys. Planetariums are developing shows that fly audiences alongside Oumuamua on its path through the solar system. Virtual reality experiences let people stand on the surface of an interstellar comet and watch the sun grow larger as it approaches. PERIHELION. But beyond education and outreach, interstellar objects are inspiring new ways of thinking about our future in space. If objects can travel between star systems, even if the journey takes millions of years, it suggests that interstellar travel might be more feasible than we thought. Not for humans, perhaps, but for robotic probes or even genetically engineered organisms designed to survive the journey. Some visionaries are already thinking about how we might use interstellar objects as stepping stones for interstellar exploration. Instead of building massive spacecraft capable of making the entire journey to another star, we could send smaller probes to hitch rides on interstellar objects passing through our solar system in the right direction. It would be slow, taking millions of years, but it would be achievable with current or near-future technology. The economic implications of interstellar object research extend far beyond the direct scientific value. The technology development, international collaboration frameworks, and public engagement strategies developed for this field are creating value across multiple sectors. The global market for space-related services and technology, already worth hundreds of billions of dollars, is being expanded by the addition of interstellar object detection and interception capabilities. Consider the value of being the first to successfully sample an interstellar object. The scientific prestige would be enormous, comparable to the Apollo moon landings. The technological demonstrations would have applications across multiple industries, and the actual samples could be invaluable for research, potentially worth billions of dollars to institutions wanting to study material from another star system. This has led to discussions about how to fairly distribute the benefits of interstellar object research. Should samples be treated as the common heritage of humanity, available to all nations for study? Or should the country or organization that obtains them have exclusive rights? These questions will become increasingly important as our capability to intercept and sample these objects improves. The detection of 3I Atlas, when it comes, will mark a new chapter in this story. Unlike Oumuamua, which we discovered late and could only observe briefly, and unlike Borisov, which behaved like a normal comet, 3I Atlas might present us with new mysteries and opportunities. Perhaps it will be detected years before its closest approach, giving us time to prepare an intercept mission. Maybe it will have an unusual composition that reveals new aspects of planetary formation. Or possibly it will be the first interstellar object we successfully sample, marking humanity's first direct contact with material from another star system. The preparation for 3I Atlas is already underway, even though we don't know when or where it will appear. Observation protocols have been refined based on lessons learned from the first two objects. Rapid response spacecraft concepts are being developed. International agreements on data sharing and collaboration are being negotiated. When 3I Atlas arrives, we'll be more ready than ever before. Looking further into the future, the study of interstellar objects will likely become routine. Just as we now regularly discover and study new asteroids and comets from our own solar system, we'll catalogue and characterize visitors from other stars. Each one will add to our understanding of planetary systems, stellar evolution, and galactic dynamics. The long-term goal is to build what scientists call a statistically significant sample. Enough objects to draw robust conclusions about the population as a whole. This might require hundreds or thousands of objects, depending on their diversity. But once we have such a sample, we'll be able to answer fundamental questions about our galaxy. How common are Earth-like planets? By studying the chemistry of interstellar objects, we can infer the composition of their parent systems and estimate how many might have the right ingredients for Earth-like worlds. How violent is planetary formation? The size, distribution, and velocity of interstellar objects tells us about the processes that ejected them. How does material cycle through the galaxy? By tracing the paths and ages of interstellar objects, we can map the flow of matter between star systems. These questions go to the heart of our place in the universe. Are we alone? Is Earth unique? Is life common or rare? While interstellar objects can't answer these questions directly, they provide crucial data that constrains the possibilities. Every piece of information narrows the range of uncertainties and brings us closer to understanding our cosmic context. The philosophical implications continue to deepen with each discovery. The confirmation that material routinely travels between star systems means that the galaxy is more interconnected than we imagined. The detection of organic molecules in interstellar objects suggests that the building blocks of life are distributed throughout the galaxy. The possibility that biosignatures could be preserved in these objects raises the tantalizing prospect of detecting evidence of life without ever leaving our solar system. As we wrap up this four-part exploration of interstellar visitors, I want to leave you with a perspective that I find both humbling and inspiring. Every atom in your body, except for hydrogen, was forged in the heart of a star. When that star died, it scattered those atoms into space, where they eventually became part of the cloud that formed our solar system. But the story doesn't end there. Some of those atoms have likely been in multiple star systems over the history of the galaxy. They've been part of planets that formed and were destroyed, comets that were ejected into interstellar space, and perhaps even other forms of life on worlds will never know. The calcium in your bones, the iron in your blood, the carbon in your DNA, these atoms have been on journeys that span billions of years and thousands of light years. The discovery of interstellar objects makes this cosmic recycling tangible. When we observe Oumuamua or Borisov or the future 3I Atlas, we're seeing part of this process in action. Material formed around one star, ejected into space, passing through our neighborhood on its way to somewhere else. It's a reminder that we're not separate from the cosmos, but part of it. Participants in a story that began with the Big Bang and will continue long after our sun has died. This cosmic perspective doesn't diminish our significance. It enhances it. We are the universe becoming aware of itself, using telescopes and spacecraft and mathematics to understand our origins and our destiny. The study of interstellar objects is part of this awakening, helping us understand not just where we came from, but where we're going. As you go about your daily life, remember that above you, beyond the blue sky, cosmic messengers are passing by. They carry information from distant stars, preserved in ice and rock for millions of years. We're learning to read these messages, to understand what they're telling us about our galaxy and our place in it. It's a remarkable time to be alive, to witness humanity's first contact with material from other star systems. The story of interstellar objects is just beginning. In the coming years and decades, we'll discover hundreds more. We'll send spacecraft to intercept them, possibly even bring samples back to Earth. We'll find patterns that reveal galactic-scale processes we can't yet imagine. And perhaps, one day, we'll find evidence that we're not alone in the universe. But even if we never find evidence of life elsewhere, the study of interstellar objects has already taught us something profound. We are connected to the cosmos in ways we're only beginning to understand. The galaxy isn't a collection of isolated star systems, but a dynamic, interconnected ecosystem where material and information flow between stars. We're part of this ecosystem, made from it and contributing to it. Thank you for joining me on this journey through the science of interstellar visitors, as we await the discovery of 3I, Atlas, and the many objects that will follow. Remember that each one is a gift from the galaxy, a message from the stars, a reminder of our cosmic heritage. The universe is knocking at our door, and we're finally learning how to answer. The age of interstellar archaeology has begun. We're no longer limited to studying our own solar system, but can examine samples from throughout the galaxy. It's a privilege no previous generation has had, and a responsibility we must take seriously. These cosmic messengers are teaching us about our place in the universe, and the lessons they bring will shape humanity's future among the stars. As Carl Sagan once said, we are made of star stuff. The discovery of interstellar objects shows us that this star stuff is constantly being mixed and redistributed throughout the galaxy. We're not just made of star stuff from our own sun's stellar nursery, but potentially from stars throughout the galaxy. We are truly cosmic beings, and the interstellar visitors passing through our solar system are reminders of our deep connection to the cosmos. The story continues, and you're part of it. Every time you look up at the night sky, remember that somewhere out there, another interstellar object is beginning its journey toward us, carrying secrets from a distant star, ready to teach us something new about our incredible universe. As we continue to watch the skies for the next messenger from the stars, we're not just doing astronomy. We are participating in a conversation with the galaxy itself, reading messages written in ice and rock, sent from places we may never visit, but can now touch through these cosmic ambassadors. The age of interstellar archaeology has begun, and we're all witnesses to its dawn.